One of the main focuses in physics is describing how things move using a model. In this video, we're going to use our model building skills to create a graphical model of one simple kind of motion. And we're going to start out by making what's called a position versus time graph. Imagine a fancy elevated high-speed commuter train that moves between two fictional cities, Happyville and Busytropolis. There are many different ways that this motion could be described. If you've been in a physics class, as you have for a while, you've probably figured out that the one scientists will be most interested in will probably involve measurement data. So here's a possible experiment to create some data. The independent variable in our experiment will be the time the train has been moving since it left Happyville. So we can measure that with any kind of a timekeeping device like a watch. The dependent variable will be the position of the train. And we'll measure its position by the kilometer markers that are alongside the track. Now, every experiment we know has to have control. And so the operator of the train will be controlling the throttle setting so that it doesn't speed up or slow down during the part of the trip that we're measuring. So that'll be a thing that's a constant, and obviously it's got to be the same train. There are a bunch of things that would have to be controlled here for this to be a good experiment. So as we're looking at this train from above, just kind of a mock-up of this train, we can see that there are different mile markers and the clock is ticking. So we can start building data in a data table for this. So we got time, we're tracking in minutes, and position in kilometers. So here's the data. At time 0, it's at position 12. And when it gets to 12 minutes, it's at position 36 kilometers. And then at 18 minutes, it's at 48 kilometers. At 30 minutes, it's at 72 kilometers. And then at 42 kilometers, at 42 minutes, it's at 96 kilometers. Now let's plot the data as a scatter plot. So we have time on the horizontal axis because it's the independent variable, and position on the vertical axis because it's the dependent variable. It's reasonable to think that a line is a good model for the motion of this train. Straight line appears to be a pretty good model. So let's look at the features of this line. First of all, the vertical intercept is 12 kilometers. This means that the position of the train was 12 kilometers from Happyville when the clock started. If we look at the slope, there's a change from 96 kilometers back from a starting point of 12 kilometers over a time change of 42 minutes. And so the slope is 84 kilometers over 42 minutes, or 2 kilometers for every minute. If the train had been moving the other direction towards Happyville on the return trip, it's not hard to imagine what the graph of position versus time would look like. And a line would still be a good model for it. And in this case, the starting position would be the 96 kilometer marker. And the train would still have a speed of 2 kilometers per minute, but because it's going in the reverse direction, the slope would not be 2, it would be negative 2 kilometers per minute. Let's define this graphical model the way physicists think about this. The vertical axis tracks the position of an object. Position is usually given the name x during one-dimensional motion, which is the kind that we have here. The train just moves along the track. It doesn't veer from side to side. So we're restricting ourselves to just one dimension of motion, which is good because the math gets really complicated when you introduce more than one dimension. The vertical intercept of a position versus time graph is the starting position of the object. This is often called xi for initial time or x0 for position at time 0. How the position changes is called its displacement. This is usually designated by delta x. Because this triangular sign, pronounced delta, it's actually a Greek letter, is a symbol that in science means change in. So delta x is displacement, which literally means the change in position. Positive displacement means the object moved in the forward direction, like the train in the first graph. Negative displacement means that the object moved in the backwards direction, like the train in the second graph. So displacement can have a positive or a negative sign depending on if the position is increasing or decreasing over time. Distance is the word we use to mean how far the object moved without worrying about its direction. It's the absolute value of displacement. So both of the trains had the same distance in the two graphs that we looked at above, but they did not have the same displacement. One was positive and one was negative. The slope of a position versus time graph has a name that you've probably heard before. It's called velocity. It's defined as the slope of that graph, so that means it's the change in position or the displacement divided by the change in time or the time elapsed. The sign of the slope indicates the direction of travel. So if it's positive slope, that means it's going in the positive direction. If it's negative slope, that means it's going in the backwards direction. The steepness of the slope is the object's speed. Because it's a ratio of how much position is changed over a given amount of time, the bigger that number is, the faster it's moving. The steepness of the slope is how fast it's moving. So speed could also be thought of as the absolute value of slope or the absolute value of position change or displacement over time, which is distance over time elapsed. This is a graph of a straight line, which means that the object's velocity is not changing over time. We're going to call this model of motion the constant velocity particle model, or CVPM for short. And that's what this unit is all about. So we're restricting ourselves to situations where the change in speed, well, there is no change in speed. This is always moving at a constant speed and a constant direction. That's a constant velocity particle model of motion. Now, it's called a particle model because we're just imagining the train as one particle. Of course, there's a beginning and an end to the train, and the individual cars are going to interact with each other a little bit. We're ignoring all that in these models to simplify, and we're just going to say every moving object is just one individual thing. The graphs of all lines have an equation that fits the pattern of dependent equals intercept plus slope times independent. So for CVPM motion, the mathematical model is position is starting position plus velocity times time. Let's qualitatively interpret what these graphs mean. So imagine that you have a position versus time graph here. Let's compare that to a different position versus time graph. What's the same is the slope. So these two objects are moving in the same direction, and they're moving at the same speed, at the same velocity. What's different between these two objects is the starting position. The one on the left, that object starts at 0. On the graph on the right, that object starts at some positive position that isn't 0. Let's make another comparison. Now we have an object that's moving at the same speed, but in the opposite direction of the original graph. Different starting point. It's now moving backwards, the one on the left, at the same speed because it's the same steepness as the graph on the right. Let's make another comparison. Both of these objects are moving in the backwards direction because the steepness of the right-hand graph is greater. That means that object is moving faster. So they're both moving backwards. They both started at the same place, but the one on the right is a faster moving object. Let's make another comparison. These two objects are moving at the same speed because they have the same steepness. The one on the right is going backwards. The one on the left is going forwards because of the positive slope. Here's another one. The new graph on the right, this represents an object that has a slope of 0, which means its velocity is 0, which means it isn't going anywhere. Its speed is 0. It's not moving in any direction compared with the one on the left, which is going forward. So just to review, a quantitative interpretation could be developed by recognizing that this graph is always going to be position is the starting position plus the velocity, which is the slope, times time. That's just the equation of a line. Another way of thinking about this is if you subtracted the starting position from both sides, you'd have the change in position or the displacement. And so the displacement is just the velocity times whatever the time change is. So for the first train, which had this graph, the equation that describes its motion, the model, mathematical model, would be position is 12 kilometers plus 2 kilometers for every minute times time. So if you put the time in minutes, multiply that by 2, you'll get kilometers. Add that to the original 12 kilometers of position, and you would predict what the position is going to be at any time for that train. For the train that was going backwards, that had the negative slope, this would be the equation that models its motion. Starting position is 96 kilometers. And then the change is negative 2 kilometers for every minute times the time. So again, input any time, multiply by 2, you get the change in position, or the displacement, in kilometers. Add that to the 96 kilometers, and you would know where the train was at any given time. So hopefully this gives you an introduction to how we can model motion, which is an extremely important concept in physics. And in future videos, we're going to build on this with some more models that help us give even more insight and give us more problem-solving tools as we go to make changes and predictions in motions.